Seismic Conceptual Design of Buildings. The reference book for this discussion is the book by Hugo Bachmann, Seismic Conceptual Design of Buildings, Basic Principles for Engineers, Architects, Building Owners, and Authorities. So first, let us have the basic principle number 1 in Seismic Conceptual Design of Buildings, which says the architect and the engineer should collaborate from the outset. So many building owners and architects are still of the mistaken opinion that it is sufficient to include the civil engineer only at the end of the design stage to calculate the structure. This is a bad approach that may have serious consequences and cause significant additional costs. Even the cleverest calculations and detailed design cannot compensate for errors and defects in the conceptual seismic design of the structure or in the selection of non-structural elements, in particular partition walls and facade elements. So it is important that there is a close collaboration between the architect and the engineer from the earliest planning stage of any building project in order to ensure a good outcome, guarantee structural safety, reduce vulnerability, and limit costs. By doing so, both partners contribute with different yet indispensable expertise. So the architect deals primarily with the aesthetic and functional design, while the engineer produces a safe, efficient, and economical structure. This is why collaboration between the architect and the engineer must start at the first design draft. So we have here a wrong one is a serial design, and a much better and more economical is the parallel design. So serial design is particularly bad and inefficient. So it is not at all efficient that the architect performs the conceptual design and selects the types of materials of the non-structural partition walls and facade elements before entrusting the engineer with the calculations and detailed design of the structure. So it is also wrong to consider seismic loading only after the completing the gravity load design and selecting the non-structural elements. So by then, the structure can only be fixed for earthquakes. So this will often result in an expensive and unsatisfactory patchwork. While a much better and more economical design is what we call as parallel design. So parallel design is much better and usually substantially more economical. So the architect and the engineer design together and taking into account the relevant aesthetic and functional requirements, develop a safe, efficient, and economical general purpose structure for gravity loads and seismic action. So they then together select non-structural partition walls and facade elements with deformation capacities compatible with the designed structure. So an optimum result can be obtained through this approach. A close and thoughtful collaboration between the architect and the engineer is therefore also of interest to the building owner. This collaboration cannot wait for the calculation and detailed design stage, but it must start at the earliest conceptual design stage when choices are made that are crucial for the seismic resistance and vulnerability of the building. So basic principle number 2 states that we should follow the seismic provisions of the codes. Unfortunately, even today, the seismic provision of the building codes are not always respected. So in the early 20th century, the first seismic provisions in building codes were introduced in a few countries with high seismicity. These early seismic codes have been periodically updated with increasing knowledge in earthquake engineering. So in the 1960s and 1970s, countries with moderate seismicity began to adapt seismic requirements in their building code. So in the same period, the better understanding of dynamic soil behavior as well as inelastic structural behavior led to the development of more advanced seismic code. So today, the principles of capacity design together with the concepts of ductile behavior allow a safe and cost-effective earthquake-resistant design. So the latest efforts of seismic code development were mainly focused on internationally harmonized standards like ISO 3010, Eurocode 8, and UBC. So this is today, the seismic provisions of the building codes are not always respected. So this is due to either ignorance, indifference, convenience, or simply negligence. So moreover, appropriate official controls and checks are lacking. So buildings that are vulnerable and at risk from even a relatively weak earthquake continue to be built today. So investigations of existing buildings showed, however, that reinforcing or enforcing the building code requirements makes it possible to significantly reduce the seismic vulnerability of buildings with no significant additional costs while improving the resistance against collapse. So the ignorance or disregard of the seismic provisions of the building codes, even if only partial, can result in an inferior building. So the reduction in value may include, among other things, the cost of retrofitting minus the additional cost that would have been incurred to ensure the seismic resistance of the building at its design and construction stage. So the designers can be responsible for retrofitting costs as well as jointly liable with the building owners for loss of life, injury, or for any resulting material damage in the case of an earthquake. A retrofit generally costs several times more than what it would have cost to ensure adequate seismic resistance of the new building. So considerable costs may also be incurred by disruptions of the building's use, such as temporary evacuation and business interruption. So furthermore, determining the responsibility of the architect and the engineer can necessitate lengthy and complex legal procedures. So the building owner, the architect, the engineer, and the authorities therefore have a vested interest in ensuring that the seismic provisions of the building codes are strictly enforced and that appropriate structural calculations and verifications are kept with the construction documents. So we have here an example. Buildings are still built with which no verification of adequate seismic resistance is conducted in accordance with the current building codes. So in the case of this masonry building right here, it appears that no adequate measures were taken. An insufficient earthquake resistance may cause a significant reduction in the value of the building and may be the cause of a civil liability lawsuit. So we also have here another picture. Buildings in which the lateral bracing is missing or highly eccentric, or buildings with discontinuities generally do not satisfy the requirements of the current building codes and are therefore likely to be damaged or collapse under the effect of even relatively weak earthquake. So basic principle number 3 says that no significant additional costs thanks to modern methods. So the opinion that designing new buildings to be earthquake resistant will cause substantial additional costs is still common among the construction professionals. In a Swiss survey, estimates between 3 and 17% of the total building costs were given. So this opinion is unfounded. In a country of moderate seismicity, adequate seismic resistance of new buildings may be achieved at no significant additional costs. However, the expenditure needed to ensure adequate seismic resistance may depend strongly on the approach selected during the conceptual design phase and on the relevant design methods. So first, regarding the conceptual design phase, early collaboration between the architect and the civil engineer is crucial. That's why we should follow the basic principle number 1. Seismic protection must be taken into consideration in the architectural design of the building, as well as in the conceptual design of the structure. Above all, substantial extra cost may be incurred if modifications and additions to the structure need to be made at an advanced stage, since they often require modifications of the architectural design also. So these may be very costly. So the second is concerning the design method. It should be stated that significant progress has been made recently. So intensive research has improved the understanding of the behavior of a building or structure during an earthquake and resulted in the development of more efficient and modern design methods. Compared to older methods, the cost of seismic resistance of a building is reduced and or the performance during an earthquake is notably improved, thus also reducing vulnerability. Of special importance are ductile structures and the associated design method named capacity design method. Thus, structural elements such as reinforced concrete walls, which are used for wind bracing, can perform other functions without notable additional cost. Fewer additional structural elements are therefore required in comparison to older methods. So we have here an example of a plan or a design. We first have here a seismic conventional design. And we have then a seismic conceptual design and capacity design. As we have observed, comparing this picture on the previous one that was shown, we can see that in this part right here, there is no structural masonry included. So now basic principle number 4. Basic principle number 4 states that we should avoid soft story ground floors. Many building collapses during earthquakes may be attributed to the fact that the bracing elements, such as walls, which are available in the upper floors, are omitted in the ground floor and substituted by columns. Thus, a ground floor that is soft in the horizontal direction is developed. That is what we call a soft story. Often, the columns are damaged by the cyclic displacements between the moving soil and the upper part of the building. So the plastic deformations at the top and the bottom end of the columns lead to a dangerous sway mechanism with a large concentration of the plastic deformation at the column ends. So a collapse is often inevitable. So we have here a picture that clearly shows the ground floor is only composed of columns. And then we also have here, sway mechanisms are often inevitable with soft story ground floor. So we can see in this photo right here that the upper part of the building stays intact while the ground floor has already been damaged. We also have here another example of a soft story ground floor that led to the failure or collapse of the entire building. So here, the front columns are inclined in their weaker direction, so the rear columns have failed completely. So the rest of the building from the second floor to the rest of the upper floors have remained intact and did not collapse, while the ground floor have partially and or totally failed. So you also have here an example of a design of a soft story ground floor. So it is feared that existing buildings such as this one could collapse even in a relatively weak earthquake because the walls are not structural only columns are made available. So now basic principle number 5 says that we should also avoid soft story upper floors. So in the previous basic principle, which is basic principle number 4, it is said that we should avoid the soft story ground floor. So we should always, or we should also rather, avoid soft story upper floors. So an upper story can also be soft in comparison to the others if the lateral bracing is weakened or omitted, or if the horizontal resistance is strongly reduced above a certain floor. So the consequence may be again be a dangerous way mechanism. So in this picture right here, we have a commercial building. The third floor has disappeared and the floors above have collapsed onto it. So you can see in this picture right here that the rest of the upper portion of the building has remained intact while an upper floor has collapsed or has disappeared. We also have here a picture. So in this office building also, an upper story failed. So the top of the building has collapsed onto the floor below. So the whole building rotated and leaned forwards. So in this picture, all the upper floors were too soft. Therefore, the ground floor has remained intact. So now let us talk about basic principle number 6. Basic principle number 6 states that we should avoid asymmetric bracing. Asymmetric bracing is a frequent cause of building collapses during earthquakes. So in the two sketches in the previous slide, only the lateral bracing elements are represented. The columns are not drawn because their frame action to resist horizontal forces and displacement is small. So the columns, which only have to carry the gravity loads, should however be able to follow the horizontal displacement of the structure without losing their load-bearing capacity. So each building in the picture presented in the previous slide has a center of mass, or the center of gravity of all masses, through which the inertia forces are assumed to act. We also have a center of resistance W for horizontal forces and a center of stiffness S, or shear center. So the point W is the center of gravity of the flexural and frame resistance of structural elements along the two major axes. So if the center of the resistance and the center of mass do not coincide, eccentricity and twisting occur. The building twists in the horizontal plane above the center of stiffness. So in particular, this torsion generates significant relative displacements between the bottom and top of the columns furthest away from the center of the stiffness, and these often fail rapidly. So therefore, the center of resistance should coincide with or be close to the center of mass, and sufficient torsional resistance should be available. This can be achieved with a symmetric arrangement of the lateral bracing elements. So this should be placed, if possible, along the edges of the building, or in any case sufficiently far away from the center of mass. So we have here in the illustration, in this new skeleton building with flat slabs and small structural columns designed to carry gravity loads, the only bracing against horizontal forces displacement is a reinforced concrete elevator and stairway shaft placed very asymmetrically at the corner of the building. So there is a large eccentricity between the centers of mass and resistance or stiffness. So twisting in the plan will lead to large relative displacement in the columns farthest away from the shaft, such as this one, and the danger of punching shear failure that this implies. So placing a slender reinforced concrete wall extending the entire height of the building at each facade in the opposite corner from the shaft would be a definite improvement. So it would be then enough to construct two of the core walls in reinforced concrete, and the rest could be for example in masonry. So this picture right here is an office building and had a continuous firewall to the right rear as well as more eccentric bracing at the back. So the building twisted significantly and the front columns failed. So we also have here in the back, this house has share a strong and stiff firewall with another house. In the front, the facade is substantially softer so that the centers of resistance and stiffness were situated at the back of the building. So the house twisted strongly in the horizontal plane but did not collapse. So we also have here, originally, the only horizontal bracing in this 70s auditorium building at Zurich were reinforced concrete walls with little torsional resistance situated at the rear of the building. So because of the considerable distance between the bracing and the center of mass of this large building, it would have twisted significantly in the plan for even a relatively weak earthquake. So the few highly loaded reinforced concrete columns in the ground floor would have experienced substantial displacements, particularly in the front of the building. So, however, the column detailing was inadequate for the required ductility. Additional steel columns were therefore built in on three sides of the building exterior. So they form a truss that can transfer the horizontal seismic forces to the existing foundation. So this upgrading also fulfilled the need for a strengthening of the cantilevered structure for gravity loads. So now basic principle number 7. Basic principle number 7 states that we should avoid bracing offsets. So horizontal bracing offsets in plane, such as the previously shown picture, or out of plane, resulted when the position of the bracing changes from one story to another. The bending moments and the shear forces induced by the offset cannot be fully compensated despite substantial additional costs. So the offsets disturb the direct flow of forces, weaken the resistance, and reduce the ductility of the bracing. Moreover, they cause large additional forces and deformations in other structural elements such as the beams and the columns and as well as the slabs. So, compared to the bracings that are continuous over the height of the building, bracings with offsets increase the vulnerability of the construction and usually noticeably reduce its seismic resistance. So bracing offsets must therefore be absolutely avoided. So the horizontal offset of the reinforced concrete wall in the vertical plane causes large additional stresses and deformations in the structure during an earthquake. So they include large local vertical forces, large additional shear forces in the slabs at offset. So redistribution of the foundation forces. No? So those were basic principles 1 to 7. Thank you so much.